Hey friends, today I will be proving that a complex analytical function is harmonic. To prove that an analytic function is harmonic, first, for any function for that matter to be harmonic, it has to satisfy the Laplace equation which says nabla square of phi is equal to 0, or a function phi which is dependent on x and y is said to be harmonic if it satisfies del square phi by del x square plus del square phi by del y square is equal to 0, which is again a Laplace equation. This is in the Cartesian form. So the double partial derivative of phi plus with respect to x, and again the double partial derivative of phi with respect to y should be equal to 0. Only then we say that the function phi of x comma y is harmonic. Now we will prove that a complex function which is f of z, which is in the form of u of x comma y plus I into v of x comma y is harmonic. For that we first consider an analytic function which is this f of z. For it to be harmonic, we need to prove that u which is the real part satisfies Laplace equation, and again v which is the imaginary part also satisfies the Laplace equation. For that, first we know that since f of z is an analytic function, it will satisfy the Cauchy-Riemann equations, that is del u by del x is equal to del v by del y, and del v by del x is equal to negative of del u by del y. Now coming to the case 1, we differentiate this first equation with respect to x and the second equation with respect to y. So when we differentiate this with respect to x, we get del square u by del x square is equal to del square v by del x into del y. That we call it as equation 3, and when we differentiate equation 2 with respect to y, we get del square v by del x into del y is equal to del square u by del y square. Now we can see that this and this both are same, so these two will be equal. So equating 3 and 4, we get del square u by del x square is equal to negative of del square u by del y square. You bring the negative, you bring this expression this side, so you get del square u by del x square plus del square u by del y square is equal to 0. So now we have proved that the real part u, which is a function of x and y, satisfies the Laplace equation, that is del square u by del x square plus del square u by del y square is equal to 0. Now we need to prove that the imaginary part v also satisfies the Laplace equation. So we come to case 2, where we differentiate 1 in the case 1 we had differentiated 1 with respect to x. Now in case 2 we differentiate 1 with respect to y and 2 with respect to x. We do the inverse of both, that is here we are differentiated with respect to x, so now we differentiate with respect to y. In case 1 we had differentiated 2 with respect to y, and in case 2 we differentiate 2 with respect to x. So now when differentiating, you get del square u by del y into del x is equal to del square v by del y square. That we have written here, and we have called it as equation number 5. And now we differentiate 2 with respect to x now, so we get del square v by del x square is equal to del square u by negative of del square u by del x into del y. Put the negative sign this side, and you can see that this del square u by del y into del x is equal to del square u by del y into del x. So that when we equate 5 and 6, we get del square v by del y square is equal to negative of del square v by del x square. When you bring this side, so you get del square v by del y square plus del square v by del x square is equal to 0, which again satisfies the Laplace equation, where v is the imaginary part and is a function of x and y, and it proved that v is a harmonic function. So from this we have proved that the analytic function f of z is equal to u of x comma y plus I into v of x comma y satisfies the Laplace equation, and hence he is harmonic. Thank you.